A remarkable event is taking place in our solar system. The interstellar Comet 3I/ATLAS, a wanderer from beyond the reach of our Sun, is making a close pass by Mars, offering scientists an extraordinary opportunity to study it up close. For the first time in history, orbiters around another planet are turning their instruments toward a visitor from outside the solar system. NASA's Mars Reconnaissance Orbiter, ESA's Mars Express, and ExoMars Trace Gas Orbiter, along with China's Tianwen-1, have all redirected their attention to follow this elusive traveler as it glides within 30 million kilometers of Mars. In this video, we'll uncover how this discovery was made, what scientists are learning from it, and what lies ahead for this mysterious interstellar visitor. Let's begin. 3I/ATLAS was first detected on July 1st, 2025 by the ATLAS Survey Telescope in Chile. At first, it appeared unremarkable, a faint, slow-moving speck, until its orbit revealed a crucial detail. It wasn't gravitationally bound to the Sun. That meant it was interstellar, traveling through our solar system on a one-time trajectory. This makes 3I/ATLAS only the third confirmed interstellar object after Oumuamua 2017 and Borisov 2019. Unlike those earlier visitors, however, 3I/ATLAS was discovered early enough to organize an extensive observation campaign. Its path brought it unusually close to Mars, making it possible for orbiters there to take part. On October 3rd, 2025, the comet passed just 30 million kilometers from the red planet, close enough for sensitive cameras and spectrometers to detect its gas and dust emissions. NASA's Mars Reconnaissance Orbiter, MRO, is using its HiRISE camera, a half-meter telescope capable of observing fine detail on Mars, to capture faint images of the comet's coma and tail. Though the nucleus is too distant to resolve directly, HiRISE may detect brightness variations and tail ripples caused by interactions with the solar magnetic field. The European Space Agency, ESA, redirected its Mars Express and ExoMars Trace Gas Orbiter, TGO, toward the event. Their instruments, including the high-resolution stereo camera and CASs, can analyze the spectra of sunlight reflected and absorbed by the comet's gases. Colin Wilson, ESA's project scientist, explained that while full detail isn't expected, these measurements could still reveal the chemical makeup of the coma and its overall activity pattern. China's Tianwen-1 orbiter joined the observation effort, adding another viewpoint from a different orbital angle. For several days, Mars became a temporary interplanetary observatory, with all active orbiters united in studying an object that formed around another star before it vanishes again into deep space. Every interstellar object offers a direct sample of another planetary system, matter shaped in a completely different environment, likely billions of years ago. 3I/ATLAS gives scientists a rare chance to compare alien chemistry with that of local comets. Observations from the James Webb Space Telescope, JWST, have already revealed a striking difference. Unlike most comets in our solar system, where water vapor dominates, 3I/ATLAS emits primarily carbon dioxide with an estimated CO2 to water ratio of 8:1. This suggests it formed in a much colder region of its home system, one where CO2 ice is abundant and stable, perhaps similar to the outer Kuiper belt, but around a dimmer or younger star. The comet's dust also behaves differently. Polarimetric observations indicate an unusually strong negative polarization, meaning the dust particles scatter light in a way rarely seen among solar system comets. This could imply compact, radiation-hardened grains that have traveled for millions of years through interstellar space. 3. I/ATLAS's environment near Mars is adding another dimension to the story. It appears to be moving through a disturbed region of the Sun's magnetic field, where charged particles twist and interact with the comet's ion tail. If Mars orbiters detect waves or distortions in the tail, it would be the first direct observation of solar magnetic influence on interstellar material. Together, these findings are building a more detailed picture of how planetary systems expel icy bodies and how those bodies evolve as they journey between the stars. Compared with Oumuamua, which behaved unpredictably and showed no visible tail, or Borisov, which resembled a typical comet, 3I/ATLAS sits between both cases, active but chemically unusual. Scientists are cautious but optimistic. Each new interstellar object broadens our sense of how different planetary systems can be and how connected they are through shared cosmic debris. The Mars flyby is only one phase of a longer campaign. After October 3rd, 3I/ATLAS will continue inward toward its perihelion, the closest point to the Sun, around October 29th to 30th, 2025. As it nears the Sun, its activity is expected to rise dramatically, releasing more gas and dust and possibly reshaping its coma and tail. Once it slips behind the Sun, observations from Earth will become impossible, but ESA's JUICE spacecraft, currently on its way to Jupiter, will step in. Between November 2nd and 25th, JUICE will monitor the comet from deep space, capturing how sunlight and temperature affect its composition over time. This will mark the first coordinated study of an interstellar comet from multiple planets and a deep space probe. These combined observations from Mars Reconnaissance Orbiter, Mars Express, JUICE, JWST, and several ground-based telescopes create a multi-point network, tracking one object from different angles and distances. This approach allows scientists to cross-verify data on its brightness, spectral emissions, and tail morphology as it reacts to solar radiation. The main scientific objective is to measure isotopic ratios in its gases, particularly carbon and oxygen. These ratios act like fingerprints, revealing whether 3I/ATLAS formed near a sun-like star or around a cooler dwarf. Even minor variations could pinpoint the kind of stellar nursery that produced it. Beyond its chemistry, 3I/ATLAS is influencing how space agencies plan for the future. Its discovery and rapid observation campaign highlight the need for quick response missions that can intercept the next interstellar object before it escapes again. Several mission concepts, including NASA's proposed Comet interceptor and ESA's similar studies, are being refined using lessons learned from this event. Still, scientists remain realistic about the limits. The comet is faint, fast-moving, and difficult to image sharply. Many results will rely on indirect measurements, changes in brightness, gas spectra, or tail orientation, rather than fully resolved imagery. Even so, these fragments of data will help refine models of interstellar chemistry and the evolution of small bodies moving between stars. 3. I/ATLAS's brief visit reminds researchers that cosmic discoveries often come without warning, and that adapting quickly may be the key to studying them before they're gone forever. The 3I/ATLAS flyby marks the first time an interstellar comet is studied from another planet. For a brief moment, Mars became our window to another star system. Its passing reminds us that even across galaxies, we are connected. As 3I/ATLAS continues its inward plunge toward the Sun, telescopes across the world remain fixed on its fading trail. Though faint, every flicker of light carries a story, a record of how matter from another star system behaves under our Sun's influence. By mid-October 2025, the comet's coma has expanded dramatically. Dust jets, driven by sublimating carbon dioxide, begin to fan out in unexpected directions, forming a lopsided halo. Observers note strange ripples along the tail, magnetic waves perhaps, twisting through the ionized gas. These distortions offer scientists a real-time look at how solar wind interacts with alien material. At the European Southern Observatory in Chile, spectroscopic data begins to arrive. Early readings confirm high concentrations of carbon dioxide and carbon monoxide, with almost negligible traces of water vapor. This finding cements 3I/ATLAS's status as one of the driest active comets ever recorded. Researchers suspect it formed far beyond the frost line of its native star system, in a region so cold that even water remained frozen solid for eons. Meanwhile, the James Webb Space Telescope captures infrared signatures that reveal something even stranger. The comet's dust grains seem to contain complex organics, carbon chains that could only form under low temperatures and cosmic radiation. While these compounds are not evidence of life, they hint at chemical pathways that may occur universally throughout the galaxy. As October 29th approaches, 3I/ATLAS reaches its perihelion, the closest point to the Sun, roughly 0.8 astronomical units away. At this distance, solar heat intensifies its activity. Jets erupt violently from the nucleus, shaping new structures within the tail. Astronomers watch in fascination as the comet brightens, its light curve rising by more than a magnitude in less than 2 days. But as quickly as it flared, the brightness begins to fade. The comet starts to move behind the Sun from Earth's perspective, becoming invisible to most instruments. For a few tense weeks, only the JUICE spacecraft, cruising between Earth and Jupiter, can track its progress. Its onboard spectrometer records fluctuations in gas emissions, while cameras measure how radiation pressure alters the trajectory of dust particles. By late November 2025, 3I/ATLAS emerges from solar conjunction. Ground-based telescopes reacquire it, now fainter but still active. The comet's tail stretches millions of kilometers long, glowing faintly against the darkness of space. Scientists compare the new data with the earlier Mars and JUICE observations, piecing together how its structure evolved through perihelion. Preliminary analyses reveal that the comet's volatile inventory has changed. Carbon dioxide output has declined, while faint traces of methane and hydrogen cyanide appear. These shifts suggest that solar heating exposed deeper, previously unreactive layers within the nucleus. Each molecule detected helps reconstruct the comet's original environment, offering a rare glimpse into the chemistry of another stellar nursery. As winter settles on Earth, observatories prepare for their final phase of monitoring. By January 2026, 3I/ATLAS will be outbound, heading back into interstellar space. Its orbit ensures it will never return. What remains are terabytes of images, spectra, and telemetry, fragments of data that will occupy scientists for decades. To the casual eye, the comet will soon vanish into the void. But for astronomers, it leaves behind a legacy. It proves that interstellar objects are not rare accidents. They are the messengers of other worlds, crossing the gulf between stars to deliver clues about their origins. The story of 3I/ATLAS is more than a chapter in astronomy. It's a reminder of how small our solar system is and how vast the universe beyond truly remains. Each encounter like this draws us a little closer to understanding the cosmic web that binds every sun, every planet, and perhaps every form of life that has ever looked up and wondered where it came from.